Now that we have an indefinite integral, let's talk about the net change theorem. Okay? To talk about the net change theorem, let's first remind ourselves the definition of an antiderivative. So big F of x is an antiderivative of little f of x if big F prime of x is equal to little f of x. Okay, so that was our definition of an antiderivative. So let's go ahead and take the integral of f of x, a definite integral from a to b of little f of x dx. So what we want to do to talk about the net change theorem and how it can be applied is what we want to do is we want to make a substitution for this little f of x. Because we know big F of x is an antiderivative of little f of x, we know that this is true. So instead of writing little f of x, we're going to write big F of x. So the integral from a to b of big F prime of x dx. So this is what we're working with. All we did was make a substitution based on the definition of an antiderivative. So let's talk about what this function here is. If we have some big f of x, some function, and we take a derivative of a function, so we take the derivative of big f of x, think back to chapter 2, in terms of an application aspect, what did we call the derivative? We called it a rate of change. Okay? So f prime, big F prime of x, is the rate of change of big F of x. So a way this can be said is the integral of the rate of change is net change. And we know from the fundamental theorem of calculus that this must be equal to big F of b minus big F of a. And this is what the net change theorem says. It says that to calculate overall net change, we only care about what the value is at the end and what the value is at the beginning. That gives you a difference. That difference there is the net change. Now, we don't care what happens in between A and B. Okay, the graph can go up, down, it can oscillate back and forth, it can keep going on a decreasing interval, slanting downwards. It doesn't matter. All we care about are the endpoints. Okay, and this can be applied because this is a rate of change. Okay, we're going to see that in the next video where this can be applied. We just need to stick a scenario with it. Okay, now let me explain the idea of net change. The example that I have is something we probably could all relate to because it deals with keeping track of your money in a bank account. Now over here is how much money is in your bank. Down here is your days. Now we're starting on day 1. On day 1, you already have $100 in your account. Okay, that's where we're starting keeping track of your money. So now on day 2, okay, it's payday. So what you do, you get paid. Let's say you get paid $120. Okay? Now, on the next day, some bills are due. You just got paid. Let's pay some $60 in bills. Now, so this is day 2, day 3. You're driving back and forth between work. You got to put some gas in the car. Now, on the next day, so this is day 4. Day 5 would be here. After this day, we'll stop. Now, on the next day, let's say it's your birthday. You go out for your birthday. You get some gift cards or something, or some cash. Let's say you pay, you get $70 in cash. But then you also spend some money on drinks. You went out, had some fun. Spent $20 in drinks. So on that day, you had a net gain of $50. You spent some, you also gained some money, but overall, it totaled out to $50. Now, let's go ahead. On day 6, let's go ahead and calculate all the money that we have so far as if we were keeping a checkbook. So we had $100 on the first day. So this is the start of our interval, day 1. And then day 2, we're positive $120. Day 3, we're negative $60. Day 4, we're negative $20. Day 5, we're positive $50. Now, if you were to go ahead and add all those up, let's see, 100 plus 120 is 220, minus 60 is 160, minus another 20 is 140, plus 50 is 190. So, on this day, if we were to calculate on day 6, calculate how much money is in our bank account. So, we have a total, it's going to go way up, $190. If we were to find the net change, see, it oscillated. It went up, then it went down, it went up again, then it went up really high. If I were to draw a graph to this, I can make it look something like that. Okay? So the net change from where you started to where you ended only matters on the endpoints. So I take the value at my one endpoint. We have $160 that day. We don't do anything. We check our bank account. We have 190. Sorry, not 160, 190. Minus, this would be like my f of a here, 100. That is a net change of $90. It's positive. I started at 100. I ended at 190. What is the difference between those two? Well, it's 90. That is the net change, the total change from the start of my interval to the end of my interval. Okay? So this is just an analogy. Like I said, we could stick a function to this, do the same thing. That's what we're going to do next. We're going to do an example. Let's see. It says evaluate the integral, find the net change. So it goes integral from -2 to 3 of x squared minus 3 dx. First, let's go ahead and draw a graph of what this is going to look like so we could see what's going on when we take this integral and we could see the areas that we are accumulating. So it's a parabola. It's a x squared. Minus 3 just means it shifted down 1, 2, 3. And if you were to solve for the roots, let's see if that's 1, that's 1, that's -2, -1, 1, 2. The root is square root 3 and negative square root 3. This is -3. See, the parabola looks something like this. All right, so let me scoot this over. Square root 3, negative square root 3. So if you look at where we're integrating from, we're integrating from -2 all the way up to 3. So I didn't go far enough out. Somewhere up there on a better drawn graph, you can get it where they intersect, maybe not so high up there. It's just because I freehanded it, but somewhere they should intersect. Let me just make this. There we go. Something like that. Now, as you can see, it splits the graph underneath the area, underneath the curve, into 3 regions. We've got this green area right here that represents positive area. We also have this here that represents positive area. And then we have all down here, which is going to be negative area. So that total accumulation is going to contribute to the net change, okay? How much do you have at the very start? How much do you have at the very end? You subtract the 2, and that is your net change. But all that means is just take the integral of this thing. Again, we'll put scenarios to it in the next video. We'll talk about with units and whatnot, and it'll probably make a little bit more sense there. Here, there's no units. It's all geometric. A little bit harder to grasp any reason why we're talking about net change. So let's go ahead and integrate this. So x squared, the integral of x squared is 1/3 x cubed. Just undo the power rule. Go up 1 power. Go up to a 3. Divide by this number. So that's where you're getting the 1/3 from. Minus 3x evaluated from -2 to 3. Okay. So if you were to go ahead and plug in 3, plug in -2, you get -10/3. -10/3. So what I'm doing here to plug these in, I'm inputting this right here into my y1, like very much similar to how you did the Newton's method. You had to put this into y1 on your y equals, so 1/3 x cubed minus 3x. And then on my calculator, I hit vars, go over to y vars, function, I choose y1, my upper bound, 3 minus y1 of -2, and then hit enter. It's going to get into a decimal. I just turned it back into a fraction. I just cleared it out. Let me show you what I mean. So 1/3 x cubed minus 3x. So input it into y1. So this is the antiderivative. So find the antiderivative here. Plug it into your y equals. And then you hit vars, go over to y vars, function, hit enter. y1 of 3 minus function vars y1 of, or vars, y vars, function y1 of -2. So then you get something that looks like this. And hit enter. And turn it back into a fraction. There you go. That's probably one of the easiest ways of evaluating a definite integral when you have bounds that just don't easily cancel. Or like if this was a 0, well, if I plug a 0 in there, it's gone. All I have to do is 3. Plugging in 3 wouldn't have been that bad. If they're 1s, plugging in 1s aren't that bad. But something like this, use the calculator. Make it a little bit easier, a little bit faster for you. You just got to watch the buttons you're pressing. Okay? So let's go ahead and do the next example. it's the integral from -1 to 1 of t times 1 minus t squared dt. So again, I'm going to draw a graph. You could always plug this in on your calculator. It'll pull up the graph for you. So I'm going to, 1's over there, 0's right there, of course. So it goes something like this. Now, this is if it's zoomed in a little bit. It goes something like that. Goes through this 0, bounces off of that 0. So here's -1. It goes down to there. Here's 1, right there. So let's go ahead and color these areas that we are going to integrate over. So from -1 to 1, we see we have a bunch of positive area right there. And then down here, since it's below the x-axis, we have a bunch of negative area right there. So this would be the total accumulation between the endpoints. You see it goes up, then it goes down. But to account for that total accumulation, or to account for that net change, we don't care about what happens in between. We only care about the endpoints. So we're going to integrate this and evaluate it at the endpoints. So we're going to have to multiply this out. We can't integrate it as it is right now. So integral from -1 to 1. If you multiply this out, let's see, you get t cubed minus 2t squared plus t dt. So square this one. After you square this one, raise the power by 1 on each term. So now that's just a power rule. We can easily undo a power rule. So go up 1 power, t to the 4th. Now what we got to do is divide by this power, 1/4, minus 2/3 t cubed, go up 1 power, then divide by that power, plus 1/2 t squared evaluated from -1 to 1. Now this one we could plug in on our calculator. However, plugging in -1 into here is not that bad. If we plug 1 into every single piece, it doesn't matter what this number is. The 1s just go away and you get this number, okay? So plugging in 1, you get 1/4 minus 2/3 plus 1/2. Minus, now I got to do -1. I got to plug -1 into here. Now plugging -1 into there is not that bad either. All -1 is going to do is possibly switch the sign of a term. If we stick it into t to the 4th, -1 to the 4th power is +1. So it doesn't do anything it doesn't change the sign of this term. So we get a 1/4. T cubed, -1 cubed, that one definitely switches sign because -1 cubed is -1. You'd have a -1 times a negative. You get a plus 2/3. And then t squared, that doesn't do anything. It's a squared, so -1 squared is a +1. So now if you look, there's a minus sign right here. 1/4 minus 1/4 goes away, goes away. +1/2 minus +1/2 goes away, goes away. But what doesn't go away is this -2/3. So -2/3 minus 2/3, that's equal to -4/3. That's a bad 4. I'll redo it. So the area, or the net change, is negative 4/3. And you can definitely see this. Look, if you draw these graphs with a little care, you can see that there's more negative area than positive area, so you should expect the net change to be negative. So from whatever you started with to wherever you ended, your total change was negative 4/3. So you should take a moment and find the net change of that problem that I have there. And all you're doing is finding the definite integral. Okay, so let's see. Refer to page 406 for application examples. Let's see. I'm on 409. Where is it? 406. All right, so if you look at 406, we can go ahead and now stick some applications to a net change theorem. Why were we going over these integrals to find the net change? So if you look at it, it says the very first one, v of t is the volume of a water in a reservoir at time t. Okay? So if water's in a reservoir, all that's saying is, here's my reservoir. It has some water level. Okay? Whatever that may be, there's waves, whatnot. Maybe there's suns. Maybe this is a very sunny place, so a lot of water is evaporating. Maybe it rains. Water fills up when it rains, okay? But this function here, v of t, measures the volume at any time t, okay? Let's see, what... At time t, they don't tell us what t is in. But anyways, v prime of t, so volume, let's say we're talking about meters cubed. Let's say our time is in weeks. Measure the water level every week. So then the derivative with respect to time, the units of it, not necessarily equal to, the units of it would be meters cubed per week. That is a rate of change. That is telling you how much a quantity is changing over time. So what we can do is the integral from time 1, whatever time you want to start at, to time 2 of the rate of change of the volume of water in this reservoir, dt, is equal to whatever the volume was at time 2 minus whatever the volume was at time 1. All this is saying is that if we start today, if we measure the volume of water today, whatever it is, and then a week later we measure the volume to find the total change, all we would do is take the final volume minus the initial volume. Okay, final minus initial. That's the idea behind this when you apply it to something. Now, we also have some other applications given in the book. They all have the same idea. You're going to get some rate, something per something time. So, let's see. There's one that they talk about chemistry. It says, if C of t is the concentration of a product in a chemical reaction at time t, then the rate of the reaction is the derivative dc dt. So then the integral of the rate of the concentration in the reaction is just equal to the concentration at time 2 minus the concentration at time 1. Final minus initial. And that's the idea behind all of these. So if you read, let's go down to population growth. Okay, if we have a rate at which the population is growing, so dn dt N is the number in your population, how big it is. So this is the rate and change of the population. If you integrate that, all that is the population at time 2 minus the population at time 1. The final population minus the initial population. The net change, the overall change from your starting spot to your ending spot. All right, so where we could apply this can be seen, let's see, net change for velocity. I had to switch back to my notes, sorry. Net change. Now, if we want to speak in terms of position, velocity, and acceleration, the net change, or what we call the displacement, remember we talked about the difference between distance and displacement. Displacement is the integral of from t1 to t2 of the velocity. Now, what we can do instead, maybe we don't care about the displacement, because remember the displacement is just how far are you away from a designated point. You may care about the displacement in, like, if you're talking about GPS, you got a destination, you don't care how you get there, as long as your displacement from where you are and the point you want to go to is 0. That would be your goal if you're trying to get somewhere. Now, you don't necessarily care the distance that you take. However, normally when you use your GPS, it's programmed to give you the shortest distance or shortest time. But what if we do this? What if we integrate from time 1 to time 2 of the absolute value of the velocity? What we get is the distance. How far did something travel? Okay. So whatever the velocity was from point A to point B, or time 1 to time 2, we can tell you how far the total distance. It could be going through loops. It could be going back. It can come back to the original starting point and go away. Now, if it came back to the original starting point after we went through this entire crazy path, the displacement would be 0. However, the distance, that'd be a different story. We did travel a really long time. Maybe we want the distance. How far did it go till it came back to its original starting spot? Now, where you would care about distance over displacement. Imagine running around a track. It's a really bad track. Let's say you start right here. Say your goal is to run a mile. Well, you go around this way. You get back here. Well, your displacement is 0. Okay? Your velocity is positive because let's say this is the positive direction. You go back, you just ran around 2 laps. Now on a standard track, you got to run around 4 laps for a mile. Now let's say you go this way now. You run 2 miles that way. Now you want to run 2 miles this way. So now you run this way. Now since we're going this way, we're going to say this is a negative direction. You're going backward down the track. You have negative velocity. So you go around again 2 times. You end up here. Now your overall displacement is going to be 0. You went 2 times around in the positive direction, 2 times around in the negative direction, ended right where you started. Your displacement is going to be 0. However, your distance, it's the absolute value of the velocity. So it didn't matter that this was the negative direction. You're still going to count it to be positive. So you did your 4 laps. You did get a mile. Okay? So that might be where you care about distance over displacement. Now let me show you graphically what this absolute value bars around the velocity is doing to the graph. So let there be time 1 right there. Let's say the graph starts here. And right here is time 2. So what you can see again, we have some negative areas. We have some positive areas. Now, if we were just doing the integral, the normal integral from t1 to t2, oh, this is the velocity at time t. V of t dt, well, if we call that area 1, area 2, area 3, area 4, and area 5, what this integral would be area 1 minus area 2 plus area 3 minus area 4 plus area 5. That's what we would be doing. Now, what this absolute value bar does is it turns all these negative areas into positive areas. That's all it does. So then